it can be a very long introduction. I'll try to keep it short. Onur is a professor at ETH Zurich, a distinguished professor there. His interest is in computer architecture mainly, but also in security, systems issues, and also bioinformatics. He has an extensive list of publications, amazingly long list of publications, and also an impressive set of distinctions. I will highlight mostly the Morris Wilks SMC GARC Award. Plus, from his research, he's been inducted in most or all Hall of Fames in the related fields of interest to this day. Onur also has been a researcher in industry. He's done applied research that found its way to products. Anyway, his bio is impressive. Again, check it online. I will not go through it. It's instructive. I would just want to pass the floor to Onur for his keynote. Thank you, Onur, for giving us the lecture.
Okay, thank you very much, Dionysius, for the kind introduction, and thank you, George, for inviting me on behalf of the organizers. Can you hear me well?
Yes.
It's all good? Okay, great. Then I will start. I'm a bit under the weather, so if you cannot hear me well, please shout and let me know. I'm also 12 hours ahead of you on the other side of the world, so it's going to be hopefully good. So I'm going to talk about RowHammer. This is something we have been working on for more than a decade, and it's kind of an interesting story of DRAM main memory and how its scaling is coming to very difficult situations. And I usually, when I introduce RowHammer to freshmen in my freshman course, I show this picture, and this picture is the picture of a bridge that doesn't exist. It used to be close to where I used to work, Microsoft Research. This is the Tacoma Narrows Bridge. And one day a bit flip happened to it. You can read about the reliability problems that caused this, but I think of this as a bit flip that leads to a reliability, safety, security issue. I also give this example from people constructing a major city after a war. And basically, they're sitting on a road over here. They seem to be very happy. But if a bit flip happens on that road, they may not be very happy in that moment. So I think we need to think about security in a much more important way, in a much more general way going into the future. And this is a quote I like that talks about security in a general way. We should really think about security as preventing unforeseen consequences going into the future. And I like thinking about this because there's a lot of discussion about the safety and security of self-driving cars today, for example. Maybe we'll have self-driving, many self-star things in the future that's going to aid our lives. We're going to depend on these. And these will see circumstances that we may not have anticipated in the future. Of course, here you can see Mr. Bean being very happy. And this is kind of his self-driving car from 1990s, early 1990s. But if something goes wrong, he may not be very happy quickly, right? So I think of these RowHammer-like reliability issues from this perspective. Now let's get into what is RowHammer. RowHammer is essentially the fact that you can induce predictably bit flips in commodity memory chips, DRAM chips. And at the time we tested, we first stumbled on the issue, more than 80% of the tested DRAM chips were vulnerable. And today it's much worse, as I will show you. And also interestingly, this is the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. So it's really a connection between hardware reliability and system security. And hopefully I will demonstrate that with many examples. And as a result, people are writing articles that look like this. This one from 2016 says that forget software, now hackers are exploiting physics, referring to RowHammer. And I think this is a very nice high-level connection that they're making between software and physics, essentially. I'm going to give you a background on DRAM reliability issues in general and memory technology scaling issues in general. Before we worked on RowHammer, we were very interested in memory technology scaling. And memory technology scaling is interesting because it's becoming much worse. Logic scaling is clearly becoming worse today, but memory has been suffering from more issues before logic, because memory is usually dominated by things that are not logic as much, let's say capacitors, for example, or interconnect. As a result, it's been seeing scaling issues much earlier. And we're going to specifically focus on DRAM, which is essentially the main memory technology that we use today in almost all computing systems. And if you look at DRAM, fundamentally it consists of a capacitor and an access transistor and sense amplification structures or sensing structures. And for this technology to work, the capacitor must be large enough for reliable sensing, and the access transistor must be large enough for low leakage and high retention time, and all of the sensing structures must work reliably. And this is charge-based memory. It's clearly dependent on the charge that's stored in the capacitor. If capacitor is charged, you encode some value. If capacitor is discharged, you encode some other value. And clearly, if you want to increase the capacity of memories we have today, we want to reduce the size of the circuitry. And we have reduced the size of the circuitry substantially over decades. DRAM was first invented in 1960s by Denard at IBM. And over time, the capacity scaling has been very successful. But more to make this capacity scaling successful, you need to reduce the size of both of these structures, capacitor as well as the access transistor and the sense amplification structures. If you reduce the size of these structures, the reliability properties become difficult to maintain. And as a result, you get a lot of noise issues. And RowHammer is one example of a noise issue. I'm not going to talk about a lot of the other noise issues, but I'll give you an example from retention time, for example. Retention time is another noise issue that essentially appears in DRAM because capacitor charge leaks over time. And there have been many studies on DRAM and its reliability. This is one study that we have done together with Facebook, again, about 10 years ago. We wanted to analyze all of the memory errors that Facebook sees in their data centers. And this is a lot of memory, a lot of computers. And this is a key picture that we have, a key data picture that we have from that study. Essentially, on the x-axis, you see the DRAM, main memory chip density employed in the server. And on the y-axis, you see the relative server failure rate. Don't worry about the exact number over here because it's a normalized number. You need to read the paper to really understand it. But basically, you can see a strong correlation between the memory chip density employed in the server and the failure rate in the server on a production data center server. And the reason is that as chips become denser, you pack more cells closer together and cells are smaller. As a result, cells are much more vulnerable to noise, so you get many more memory errors. And if you're interested, this is the paper we wrote about the topic in DSN in 2015. So we've also been building a lot of infrastructure to understand issues related to memory reliability and memory technology scaling. On the right bottom over here, we show the earliest infrastructure that we built. These are FPGA-based infrastructures that enable us to test modern DRAM chips. I'll give you some references related to it. This is where we did a lot of the original RowHammer studies, which I'm going to talk about. And we have actually open source released this infrastructure. And we actually have a new version of it that's called DRAM Bender that was released much more recently at the end of 2022. I don't have a reference over here, but if you search for DRAM Bender, you can find it. So if people are interested in actually doing studies of the sort that I'm going to describe later, we'll be happy to support it. And they're actually relatively easy to do as long as you have an FPGA and you use this sort of infrastructure. And this is the original infrastructure that enabled a lot of the studies. And the main reason we actually built this infrastructure was initially to study retention issues in DRAM. As I said, DRAM is charge-based memory, and charge leaks over time. As a result, if you don't refresh DRAM cells, you lose the charge. You lose the data value that you stored in DRAM. That's why DRAM is called dynamic memory. It needs to be refreshed dynamically, periodically. But we asked the question, and as you reduce the size of the DRAM cells, you need to refresh it much more frequently. So refresh rates 10 years ago is much lower than refresh rates today, actually, in modern memories. And clearly, refresh is a problem because as you refresh memory, you're increasing the energy consumption, you're causing performance issues and quality of service issues. So one of the reasons we built this infrastructure was to understand these retention issues. And we asked the question, do you have to refresh DRAM periodically every 64 milliseconds, all of DRAM? And the answer, it actually is not necessary to do so because there's a huge variation in the retention time profile of DRAM because of manufacturing variation, process manufacturing variation. So some cells need to be refreshed very frequently, but a vast majority of cells don't need to be refreshed very frequently. So if you can actually understand what's going on inside the device, you can build a memory controller or an operating system, some software or hardware that can actually get rid of most of the refreshes. Of course, it's not that easy. It turns out the refresh rate, the retention time of a DRAM cell not only depends on the location, but it's also dependent on the data value that's in the DRAM cell and around the cells, in the cells around the DRAM cell. It's also dependent on time. So there are some random effects that affect retention time. These are quantum-like effects that are actually very hard to predict. So we actually did a lot of studies using our infrastructure, which I'm not going to bore you about. I'm just going to flash some of the works that we have been doing in terms of retention, which is quite fascinating in my opinion. It's actually related to the RowHammer, as we will see, but it's a different kind of failure mechanism. And if you're interested, you can clearly find out a lot more information on this topic. But these are some of the studies that are enabled by this sort of infrastructure. So while we were working on these studies, we actually wanted to test other issues in DRAM. And as I will show you later on, we had a flash memory-based infrastructure also, and we did test a lot of error mechanisms for SSDs, modern solid-state drives as well. And we found out a lot of interesting issues over there. And this catalyzed us to think about what other failure mechanisms may exist in DRAM. And that's what led to RowHammer essentially. And as I said earlier, RowHammer is the fact that you can predictably induce errors in most DRAM memory chips. And it's a simple hardware failure mechanism that can affect system security vulnerability. Now, let me give you what it is essentially. It's essentially a read disturbance phenomenon. So if you look at DRAM, it looks like this. You have a bunch of rows. And in order to access some cells in one row, you need to apply high voltage to that row. Essentially, it's called an activate in DRAM. And if you want to not access those cells anymore and access some other cells, you apply low voltage to this row. This is called an precharge in DRAM. Now, if you keep doing this repeatedly, activate, precharge, activate, precharge, activate, precharge, activate, precharge, and you need to do this when you're reading from DRAM actually, it turns out some cells in adjacent rows that are vulnerable get flipped. If you do it enough times, if you do this precharge and activate enough times before the cells get refreshed. Now, this is read disturbance. Clearly, this should not be happening because we're not touching these cells that are marked X over here. We're actually only touching the cells over here, and we're just reading from these cells. Clearly, we should not be changing any other value in memory, including the values inside this row. So that's why this is a data corruption issue, as you can see. We call this the hammered row. We call the adjacent rows the victim rows. And we basically tested a number of 129 modules from 3 major manufacturers. There are only 3 major DRAM manufacturers in the world today. And we show that more than 80% of the chips that are manufactured by these companies are actually vulnerable to this effect. So it's actually an industry-wide problem. It's not just one manufacturer. It's an industry-wide technology scaling problem. It's a technology scaling problem because you can see over here that earlier modules did not have this issue. Error rates are low when you actually do this precharge and activate. But all of the modules that we tested that were manufactured between 2012 and 2013 are actually vulnerable. So we could see this effect in newer modules. And as I will show you later, modules that are manufactured in 2020, 2019 are actually a lot more vulnerable. So it's a technology scaling issue because in past DRAM technologies, in past DRAM incarnations, you could not do enough activations before the cells get refreshed to induce these bit flips. The bit flips happen because you're able to do enough activations so that you deplete the charge from adjacent cells. I'm going to talk about this very little right now. So why is this happening essentially? Essentially, DRAM cells are too close to each other. They're affecting each other in complicated ways. They're not electrically isolated from each other. Access to one cell affects the value in nearby cells due to electrical interference between the cells as well as the wires used for accessing the cells. Now, there are multiple issues that lead to RowHammer, but the cell-to-cell coupling or interference is one of the major issues. I'll give you an intuitive example. When we activate or apply high voltage to a row, an adjacent row gets slightly activated as well because these word lines are too close to each other. As a result, vulnerable cells in that slightly activated row lose a little bit of charge. Now, if you keep this row hammering, if you keep doing this hammering enough times, charge in such cells get drained. And if the cells don't get refreshed before that charge gets drained, you would lose the data value. So you would get data corruption essentially. Now, we will see that this data corruption actually leads to a security vulnerability in addition to being a reliability issue. Okay, so basically the higher level implication is that you have a huge implication on the transformation hierarchy, which is affecting the algorithms as well as the security of the system, because these bit flips can be actually used by some malicious programs to take over the system, as we will discuss, to bypass the virtual memory protection mechanisms that rely on physical isolation between different, essentially, pages in the memory. Okay, by the way, feel free to ask questions. I'm not seeing any faces because I'm just seeing my presentation right now. If people would like to ask questions, you can interrupt me I'm happy to accommodate the questions while I'm talking. So basically, when we wrote the paper, we also showed that this very simple x86 program can induce many errors in real systems. You can see that this program, what this program does is, you can actually download this program. An improved version was developed by Google, and you can download it. And many other attacks were developed based on this program in the future, with, as I will talk about later. You can download actually much better versions of this program. But the basic idea in this program was to select addresses X and Y such that they fall into the same bank, and bypass the caches, and bypass the row buffer in DRAM, such that you would basically ping pong activates to these two rows in DRAM, X and Y. And then if the chip is vulnerable, you would get bit flips in the chip. And we actually showed that you could do this in real systems, real Intel and AMD systems. And there's nothing special about Intel and AMD, only all of the systems that have good enough memory controllers, which all systems today actually have, see bit flips in such real systems. So this is a real reliability and security issue, as we will also see in a little bit. And when we actually first wrote the paper, we said that memory isolation is a key property of a reliable and secure computing system, and access to one memory address should not have unintended side effects on data stored in other addresses. And I actually strongly believe that still. I think we should have some sort of root of trust in hardware that requires memory isolation. And we said that if actually some malicious attacker can use these bit flips to hijack your computer. And while we were working on this, the good folks from Google Project Zero, Mark Seaborn and Thomas Dulien, published a blog post that essentially showed this. And I would recommend people who are interested in system security in general and systems in general to read this blog post, because it's a beautiful blog post. They also have a black hat presentation. And I just copied and pasted some things from this blog post onto this slide. They basically replicated what we found in our paper. And they built two working privilege escalation exploits to exploit RowHammer, essentially. One takes over the Google native client. It's interesting. We will get back to it at the very end of this talk. It essentially takes over a kind of sandbox virtual machine. The other one's even more interesting because it takes over x86 for Linux using RowHammer-induced bit flips. So a user-level program can actually become root on x86 for Linux. And the way they did this was not easy. It's a probabilistic attack, but they were able to induce bit flips and page table entries of this program. And by carefully spraying the memory with a lot of page tables, by opening a file many times, they were able to gain write access using this user level program to the program's own page table. And if you gain write access to your own page table as a user level program, then you essentially all bets are off. You can gain any kind of access to the system. And that's how they showed that RowHammer is actually a serious security threat. And people started writing more papers. I'm going to reference some of these soon. And people start drawing pictures like this also. I like this one part in particular. And there's a famous hacker on the internet characterized RowHammer as breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations opened the door you were after. So unfortunately, I cannot be with you today, but if the doors over there in that room are locked, and if you want to escape from that room, you might want to start banging on the walls. And if RowHammer is in effect, the vibrations that are caused by your banging may magically open the doors. Of course, that's a joke, but that's essentially, I think, an interesting analogy. Okay. After this, a lot of people in the security community designed a lot of interesting attacks. I'm not going to go into the details of these attacks. I find a lot of these fascinating. These folks from TU Graz showed that you can actually take over a remote machine using RowHammer bit flips in JavaScript. These folks showed that you could actually take over a mobile phone on an ARM-based system by taking advantage of the deterministic memory allocation patterns of the Android operating system and fooling the operating system to allocate page table entries of a user-level program to locations that they know are vulnerable to RowHammer, and then hammering those page table entries after that. They actually had a nice application also. These folks show that you could actually accelerate these attacks using GPUs and do these through the WebGL interface. These folks show that you could do these through the remote direct memory access engine on a remote computer. These folks show essentially the same thing. And these folks show that even if you're not able to take over a system using RowHammer, you could break confidentiality. You can use RowHammer bit flips to read data that you don't have access to. So it's also a confidentiality issue, as you can see from this work. More recently, there are actually multiple works showing that using RowHammer, you can turn an otherwise quite reasonable, quite good neural network to something completely inaccurate. And I'm not going to go into details again of these works. There are multiple different ways of doing these fault attacks using RowHammer. And these folks show that otherwise good network with reasonably high accuracy can lead to something very low accuracy because you have bit flips in the weights of the neural network, essentially. Okay, I'm going to skip some of these, but maybe there are other security implications. Once you actually have a lot of bit flips in your computer, there could be other security implications. And this is another picture that I took off the internet that talks about RowHammer, essentially. We have written a survey that covers a lot of these works that go until about 2020. If you're interested in that, this actually is a very high coverage survey. If you're interested, this covers all the way from circuit level, device level to systems level, which is quite interesting. And more recently, we've augmented it with a recent update that is already on archive, and it's going to be presented next week in ASP DAC. But now let me go into a little bit more detail on what's happening and how can we make sense of it and how can we fix it, essentially. But I'll first jump into understanding, and feel free to ask any questions, as I said. So this is the paper that introduced the issue. And we did a lot of studies with the infrastructure that we built that I mentioned earlier. We tested more than 120 modules from 3 major manufacturers. I'm going to give you some key results that are important for multiple things, both understanding the problem as well as solving the problem. There are many, many results in the paper that I'm not going to talk about. But one interesting result is this. What is the adjacency between the aggressor and victim? And this is from the perspective of the memory controller. So a memory controller has some row addresses, and it can observe the bit flips. It can hammer one row, and it can observe bit flips in another row. So what is the distance in terms of the row addresses between the aggressor row as well as the victim row? And these are from the worst modules for 3 different manufacturers. And this shows the distribution. Normally, you would expect the distance to be -1 or 1 because a row has 2 adjacent rows at the upper side and the lower side. But and that's what we see most of the time. But in some cases, we see that there are some non-adjacent rows getting bit flips. And the major reason here is that because the memory controller has a different address space than the DRAM. Internally, the DRAM chip remaps some of the rows to some other rows because there are some other faults that are happening, and internally, DRAM manufacturer remap those rows. So from the perspective of the memory controller, you do not know essentially which rows are perfectly physically adjacent in DRAM. So this is going to limit some of the solutions that are on the memory controller side because the memory controller now cannot know exactly which rows are physically adjacent. The DRAM chip knows this information, but that information doesn't get communicated to the memory controller normally. So this is important from that perspective. Let's take a look at another experiment we did. These are all experimental results from real DRAM chips. Again, worst DRAM chips from 3 major manufacturers. We're going to look at the access interval, how often you're activating a particular row. There's some frequency that's not allowed in the DRAM standard. And you can see that as you reduce the activation frequency, you get fewer errors. And this is expected because as you reduce the activation frequency, you're reducing the number of hammers that you induce on a given row. And less frequent accesses lead to fewer errors. So this shows that the RowHammer is actually an access pattern dependent problem. And this could be one solution. One solution could be saying that you're not supposed to access a row more than some frequency. But this is not a good solution because this would actually significantly hurt performance, as we have shown in this work. And then the next study is refresh interval. What happens if you actually increase the refresh rate or reduce the refresh interval or decrease the refresh rate or increase the refresh interval? 64 milliseconds was the standard at the time. Today, it's 32 milliseconds, and we're marching towards 16 milliseconds in the future. So as expected, as you reduce the refresh interval, meaning increase the refresh frequency, you get fewer errors. But if you want to get rid of all of these errors by increasing the refreshes, you have to increase your refresh rate by 7x. And this is data from 2012. Today, it's actually much worse. So increasing the refresh rate is not a good solution to RowHammer, but that was the earliest solution employed in modern systems. Okay, there's also other studies that are quite interesting. So there's data pattern dependence. If you look at the left figure, there's some data pattern. If you look at the right figure, there's some other data pattern. And the right figure, the data pattern that actually induces a lot more capacitive coupling between the cells, lead to a lot more errors. So there's an order of magnitude difference between the right and the left figures. And this is because there's a lot more capacitive coupling. And if there's a lot more capacitive coupling between the DRAM cells, you have a exacerbated RowHammer effect. And this is actually true for retention time also. So there's a lot of synergy between retention time studies and RowHammer studies in terms of data pattern. So there are a bunch of other key observations. It's true that there are some interesting corollaries, analogies between retention time and RowHammer, but these are actually completely different phenomena. So they're very different failure mechanisms. We know exactly why retention time happens. RowHammer is a little bit more mysterious and a little bit more complicated, let's say. Errors are repeatable. This leads to this being a security problem. You can actually repeat these errors. If a cell, if you can induce a bit flip in a cell, you can induce it again. This actually, as a result, you can actually template memory and you can figure out which cells are vulnerable. And you can be a, let's say, sneaky attacker who can learn this information over time and actually use it whenever the time is, let's say, ripe, when you know that information. We get as many as 4 errors per cache line at that time. Recent data shows that this is getting much worse. As a result, simple error correcting codes cannot prevent all errors. So you need to be actually paying a lot of overhead to prevent all errors. And cells are actually affected by aggressors on both sides. So this is double-sided hammering. We observed this in our earlier initial paper, but this double-sided hammering actually leads to many more errors, RowHammer errors. I'm going to talk about many-sided hammering a little bit later. So if you're interested, there's a lot more in the original paper that I'm not going to talk about right now. But I will soon talk about some recent studies that show that RowHammer is getting much worse. I'm going to talk about this. And there are many dimensions to RowHammer. And we're going to examine some interesting effects very quickly as well. Now, before I jump into those recent works, let me talk about RowHammer solutions. But at this point, are there any questions?
Yes.
Okay, so, please.
I think it was on the slide 65, if I remember correctly, and it had to do with the refresh rate of, yes, this one.
Yes.
So we're moving. You said that we are on 32 milliseconds, and we're moving towards 16. Just a clarification. You said that. It's a good thing that we're moving towards higher frequencies of refresh, right?
Yes.
You're actually tackling the problem.
So that's a very good question. Yeah. So yeah, higher frequency of refresh can actually fix the problem, but as I will show you soon, RowHammer is also getting much worse.
All right. Okay.
So within a refresh interval, let me give you some numbers over here. At 64 milliseconds, I believe you could do 1.4 million activates or something around that number. And RowHammer happens, we showed that you could actually get RowHammer after 140,000 activations. But today, I will show you some recent results. You can actually induce bit flips after about 10,000 activations, which you can easily do within 16 milliseconds, or even 8 milliseconds, or even 4 milliseconds.
All right. So the picture I get from this one is not as good now, right?
Exactly. Right. Basically, these curves have shifted to the left a lot today, even though the refresh interval is reducing.
All right. Yeah. Thank you.
Sure. Okay. That's a very good question. So let me move on. Refresh and RowHammer are actually very interesting to examine together. Okay, so let me talk about RowHammer solutions. So clearly, if something like this is discovered, there are 2 types of solutions that one wants to develop. One is immediate, because there are clearly vulnerable DRAM chips in the field. What can you do to fix that problem? Clearly, there are limited possibilities today, especially because our memory controllers are not very programmable. I'm going to advocate for that towards later parts of this talk. But then there are also longer-term solutions that we can develop to protect future DRAM chips, hopefully completely securely. And here we have a wider range of protection mechanisms. In our original paper, we discussed both types of solutions. I'm going to talk about these a little bit. There are 7 solutions in total. I'm going to talk about the best solution at the time we envisioned to be good. But because RowHammer became so much worse today, I don't believe that the solution is good enough. Actually, we have shown that it's not good enough today. But let's cover some of the solutions. Clearly, making better DRAM chips using better materials, better isolation is great if you can do it at low cost. Unfortunately, people have not found low-cost methods of doing it so far. Refreshing frequently, again, this has power performance issues. We're marching towards that because the DRAM cells are becoming smaller, but still, RowHammer requires a lot more frequent refresh than regular periodic refreshes. As a result, I don't think this is a good solution, and we will show some results related to that as well. I've already shown you some examples. Sophisticated error correction codes, unfortunately, again, you need to correct a lot of errors, as I will show you more than 7 errors per cache block. This is going to be very expensive if you want to employ that. And also, error correcting codes are good when you don't know the reason for the errors in general, like random errors. RowHammer, we know the reason for the errors. So, but access counters, I think, is an interesting solution, and people have been employing this in the field, even though they have cost, power, and complexity. So, figure out the number of accesses that you're getting to a row, and refresh adjacent rows or throttle victim rows before you actually induce bit flips because you have had too many accesses to that row. That's the idea over here. The question is, can you do this efficiently? Okay, so these are not immediate solutions, as you can see, except for the refreshing frequently. So refreshing frequently was the only immediate solution, and that was actually employed. This is Apple's security patch from about 2015, I believe, and you can find it online also. They basically said, acknowledge the problem, and they said that they increase the memory refresh rates. They didn't say how much. I believe they increase it by 2x, which kind of closes the gap, but clearly it doesn't get rid of all of the errors. And they were nice enough to cite our paper over here. So our solution was required some changes to the memory controller. It could be implemented in the memory controller DRAM. The basic idea is it's a probabilistic solution, basically. The basic idea is after closing a row, the memory controller activates or refreshes one or both of the neighbors with a very low probability. These are potential victims, essentially. And you can see the probability. And if you actually are paranoid, you can change the probability. And we showed in our paper that you can get a very good reliability guarantee with P equals 5 out of 1,000. Okay, so this is actually interesting. As I said, we believe that this was actually a good solution. And this could be done in the DRAM chip. It's actually done in some DRAM chips today, as we will see later on. Initially, it was implemented in memory controllers. In fact, Intel memory controllers implemented a version of this. You can see a screenshot of the BIOS. And in the BIOS, you can actually pick your RowHammer solution. You could either pick 2x refresh in this particular case or hardware RowHammer protection. And if you pick hardware RowHammer protection, there's an RowHammer activation probability at which you can induce adjacent row refreshes. This is not exactly how we envisioned it, but this is a version of probabilistic adjacent row activation. Now, this is actually interesting. I think this was a step in the right direction. But DRAM manufacturers at some point said, we sold RowHammer. So as a result, these memory controller-based solutions were disabled or not developed going into the future. So we're going to get back to that soon. But I believe this is a step in the right direction. And this sort of intelligent controllers that try to understand what's going on or try to probabilistically prevent these errors are important for security, safety, reliability, and scaling, as we will discuss later on as well. Here, I will take a segue. This sort of intelligent controller actually exists for flash memory. So if you actually use SSDs, which everybody, I believe, is using SSDs today, if you have cell phones or smartphones, and these SSDs have flash memory. And NAND flash memory is actually a very, very vulnerable technology. It has lots of error mechanisms. And we've been doing a lot of studies on this topic. I'm going to mention one paper very briefly. But basically, you have an intelligent memory controller in an SSD controller that predicts and overcomes these reliability problems. And if you're interested in a modern SSD controllers and what kind of error characterization, mitigation, and recovery mechanisms exist, this is a paper that we wrote a few years ago that talks about this issue. Okay. Now, after flashing these papers, let me talk about what happened to RowHammer in 2020 and 2022. Because, as I said, people were developing solutions, and at some point, DRAM manufacturers said, we solved the problem. And RowHammer is not there anymore. Clearly, some people believed it, but we were skeptical as scientists. So we actually decided to revisit what's happening in RowHammer. And we revisited in multiple ways. I'm going to talk about some circuit level or device level studies first. where we turned off the solutions and we wanted to understand the vulnerability from a very fundamental perspective. We wanted to understand what's happening to the DRAM cells. And these are the key takeaways from more than 1,500 chips. Basically, we found out that newer DRAM chips are much more vulnerable to RowHammer. You get more flips that are happening earlier. Essentially, there are new chips whose weakest cells fail after only 4,800 hammers. This is double-sided hammering, so you actually have 9,600 hammers on both sides total. And chips of newer DRAM technology nodes actually are much more vulnerable. And existing mitigation mechanisms are not effective at future technology nodes. So if this scaling becomes much worse, which is going to become worse because cells are becoming closer and smaller as well as closer to each other. So there's no reason to believe that RowHammer is going to become better unless there are some solutions internally developed. These mitigation mechanisms are not going to work well. So we actually built a bunch of new testing infrastructures to test this. And I'm not going to bore you with the methodological details, but you can find out information about this in the paper. I'm going to show you one picture over here. This basically shows on the x-axis the hammer count, and y-axis shows the RowHammer bit flip rate. And you can see that old technology, in old technologies, you see a curve, this blue curve over here for one manufacturer over here. And this curve shifts to the left and up higher with the newer technology, meaning that you get bit flips earlier at smaller hammer counts, and you get more bit flips. And you can see this trend in all of the manufacturers. This is average across many, many chips in all manufacturers. So basically, this shows that RowHammer bit flip rates are actually increasing with technology generation. You're getting RowHammer bit flips with earlier with smaller hammer counts. This also shows that smaller hammer counts over here, but again, I'm not going to talk about this in more detail. So it's fascinating. In our original paper, we showed that more than 100,000 hammers were required to get a bit flip. Here we show that you get bit flips after 4,800 double-sided hammers. And we actually evaluated many mitigation mechanisms that were proposed until 2019 at the time. And we showed that none of the mechanisms either scale to smaller number of hammer counts to induce bit flips, or they induce very, very high overheads. For example, this curve over here is increasing the refresh rate. At some point, it becomes unreasonable. You can see that the system performance loss is 80%. So you get 5x reduced performance if you actually keep increasing the refresh rate to tolerate the RowHammer bit flips that you get. Some other solutions like Para, for example, probabilistic adjacent row activation also doesn't scale very well. If you get into hammer counts that are on the order of 1,000, for example, you get about 25% system performance loss over here. And again, this depends on the applications. Of course, some heavy applications see a lot worse results. Okay, so that was revisiting RowHammer at a lower technology level. And we showed that it's getting much worse. Feel free to, again, interrupt me if there are any questions. And we also wanted to understand whether the solutions that are actually developed by the DRAM manufacturers are secure. And clearly, they claim that they were secure. And in this paper, we showed that these solutions actually do not work. We call this TRRespass. The reason it's called TRRespass is TRR was the name of the solutions that were developed. It's called target row refresh. This is defined in the new DRAM standard to take into account RowHammer DDR4 standard. It's not clearly defined how exactly it works. Basically, it was more security by obscurity. DRAM manufacturers said that, okay, we implemented TRR and there's no RowHammer anymore. But they didn't say exactly how it works. And we decided we wanted to actually understand how it works internally. So this work introduces the many-sided RowHammer attack. And the idea here is to hammer many rows to bypass the internal target row refresh mitigations. So internally, we found out that this target row refresh has some tables. And these tables keep track of some aggressor rows. And these tables have limited capacity. So if you can somehow hammer enough rows to overflow these tables become useless. So the mitigations that are internal to the DRAM chips can be bypassed relatively easily. So to be able to do this, we need to reverse engineer the mitigation mechanisms that are implemented in the DRAM chips and the memory controllers. And we actually reverse engineered this partially, enough to show that you get bit flips in all major manufacturers' chips. And we provide an automatic tool that can effectively create many-sided RowHammer attacks. Later, we're actually improved this tool to show that DDR5, more recent DDR chips are actually also vulnerable. So this is an example of many-sided hammering pattern. So if you look at the red rows over here, those are the rows that are hammered. You keep activating them and pre-charging them. And here you have a 3-sided pattern. Here you have a 4-sided pattern. if the tables, for example, if you have a 4-sided pattern and if you have a 3-entry table or 2-entry table, you would overflow that table. And these are real results. For example, in some chips, we get bit flips after 9-sided hammering. You don't get bit flips until 8-sided hammering, for example, because at some point you overflow the tables. Okay, so to be able to do this, we had to understand what's going on inside the chip. So our infrastructure was very helpful for this. Let me just give you a quick idea of how In-DRAM target row refresh works. There's a sampler component and there's an inhibitor component. Sampler tracks aggressor row activations inside the DRAM chips. And this could be based on frequency. This could be based on time. This could be based on some random seed. And there are actually different variations of it that implement by different manufacturers. I'm going to mention that in a later work that I'm going to talk about. Regardless, the sampler has a limited size. And that's what we're exploiting over here. Because the manufacturers did not really prove that this is secure, they had a limited size sampler. And if we can overflow it, you cannot keep track of some rows that are going to be hammered. As a result, an attacker can take over the system. Of course, inhibitor essentially prevents bit flips by refreshing victim rows, but it requires a sampler to accurately track aggressor rows. So it doesn't work if the sampler is, let's say, compromised. Okay, and this is a huge table from our paper. You can see that there's some best patterns that are 19-sided. So you need to hammer 19 rows to get the best number of bit flips. And you can see that in this paper, we were not able to bypass all chips. But later work actually bypasses all chips if you actually reverse engineer more carefully. I will talk about that. But this was good enough to show that some on real cell phones you could induce bit flips, and you could actually do real RowHammer attacks. So these are real RowHammer attacks, 3 major RowHammer attacks in the field. One is basically taking over the Linux kernel. That's a page table entry attack. This is the RSA attack is essentially getting a private key using RSA. But you can see that the attacks were possible on DRAM chips that are supposed to be secure. Okay, I'm not going to talk about this in more detail, but feel free to, again, read the paper, ask questions. So basically, these results were just scratching the surface. And we said that there's a lot of room for uncovering more vulnerable chips and phones. And essentially, the mitigations advertised as secure are not secure because these mitigations are security by obscurity. And this is likely not a good solution going into the future. And we argued for more openness in the industry to solve these problems. We're going to talk about that also. So essentially, at this point in 2020, we show that industry-adopted solutions do not work. And existing mitigations in industry and academia are not going to scale well into future chips because RowHammer is becoming much, much worse going into the future. We also asked the question, how do you guarantee that Oh, yes, please. Hello? Yes. I can hear you.
We have some networking problem. We're fixing it.
Okay.
Yanni, okay, we're back.
Okay. Okay, it's good, right?
Can you still hear us?
Yes, I can hear you.
All right.
I don't see the camera anymore, but I can hear you.
Oh. What about now?
Okay, the camera is good.
We're back.
Okay, so should I continue from here, or are there any questions?
Yeah, it was just 1 minute of disconnection, so we are fine.
Oh, okay, okay. So, okay, just to say that basically this work showed that by this time in 2020, it was clear that the solutions that are adopted in industry do not work. And also, RowHammer is getting much worse at the device level, and the solutions that are developed by both academia as well as an industry are not going to scale well into the future. We also asked the question, can you guarantee that a chip is RowHammer free? I'm not going to talk about this in detail. It's actually a very tough problem. And we wrote this paper together with Microsoft folks that showed that it's very difficult to guarantee that a chip is RowHammer free. But this is a problem that actually industry is quite interested in. How do you guarantee RowHammer free chips? And if people are interested, they may want to take a look at the paper. Later, we wanted to really understand whether we can uncover target row refresh mechanisms almost completely. And that's what we did in this micro paper in 2021. And micro was supposed to be in Athens, but because of COVID, unfortunately, we couldn't come to Athens, so it was virtual. In this paper, we wanted to really understand, we developed a new methodology that leverages data retention failures to uncover completely the inner workings of target row refresh and study its security. I'm going to mention the basic key idea soon, but the key conclusion of this paper is that if you understand the underlying protection mechanisms completely or almost completely, you can craft RowHammer access patterns that is specific to the DRAM generations or chips by a certain manufacturer. And as a result, you can bypass all the mitigations that are in all modules. And we show that more than 99.9% of rows in a DRAM bank experience at least one RowHammer bit flip. And you get up to 7 RowHammer bit flips in an 8-byte data word, making ECC error correcting codes completely ineffective. And you need very strong error correcting codes to actually protect the chips. So the key conclusion of this work is that TRR does not provide security against RowHammer. And hopefully we can, by having the openness of this infrastructure, which is actually fully open source, you can use this infrastructure to test your own DRAM chips if you're interested. You can develop better protection mechanisms. And the key idea over here goes back to the retention failures that we have studied in the past. Basically, internally, the DRAM chip refreshes some rows. And to understand how the internal mechanisms behave, we can look at the data retention failure patterns in DRAM by turning off refresh. So if you turn off refresh, if you expect a row to fail because you turned off refresh, if the row doesn't fail, now that's an indication or is a side channel that DRAM internally is refreshing a row to protect against RowHammer. And by taking advantage of the side channel, you can figure out how the underlying RowHammer protection mechanism behaves. And that's the basic idea. If you're interested in the details are in the paper. So for this, we use a DRAM vendor infrastructure that I mentioned at the beginning. And we tested a bunch of chips, and we found out that all of them are vulnerable. And this table kind of summarizes what we found out for real DRAM chips. So you can see that different manufacturers, A, B, C, use different mechanisms. Some of them use counter-based aggressor detection. Some of them use sampling-based. Some of them use a mix. The capacities are different. Some of them have per bank mechanisms. And there are a bunch of differences, basically. And regardless of the differences, you can overcome the mitigations. And you can induce many, many bit flips in real DRAM chips if you know what's going on underneath, basically. And as I said, ECC is not a good protection mechanism. And this figure shows that ECC does not work. OK, there are many more results in the paper. I'm just covering a lot of papers relatively quickly because we don't have a whole lot of time. But if you're interested, again, you can read the paper or download the source code. You can find the source code online, or you can feel free to email me. So the hope is that this sort of infrastructure that can methodically understand what's going on inside the DRAM chip can enable much better future solutions and security assurance of real DRAM chips as well. Because DRAM chips are actually used everywhere, including automotive industry. And I've shown you a picture of Mr. Bean driving his own self-driving car. And if these DRAM chips are vulnerable, you need really security assurance solutions in the field as well to make sure that these DRAM chips don't cause security problems or safety problems in operation. Okay, now let me switch gears a little bit. We have also been investigating new RowHammer characteristics, and actually this is going to be more important in the future, in my opinion. This work shows that RowHammer has many dimensions. We examined 3 fundamental properties that affect RowHammer: temperature, aggressor of activation time, and physical location of victim DRAM cell. And our goal is to really find effective and efficient attacks as well as defenders. If you really understand the effect of temperature, for example, you could use it from the perspective of the attacker as well as the defender. Again, we used our infrastructures to understand these effects. Here, these experiments actually take a very long time, so we tested fewer DRAM chips. And you can see there, in this case, we actually included the 4th major manufacturer as well. They have a small market share, but they exist. Let me give you this takeaways. Basically, we found out that a RowHammer bit flip is more likely to occur in a bounded range of temperature. So the relationship between RowHammer and temperature is actually complicated. It's not as simple as retention versus temperature. The retention errors, for example, increase exponentially with temperature increases, but that's not true in RowHammer. In RowHammer, there is a bounded range of temperature where each cell is vulnerable, and this range of temperature is different for different cells. If the aggressor row is kept active for a longer time, there's some buildup that happens that lead to more RowHammer errors. This is actually very interesting. I will not spend a lot of time, but it's an interesting observation. And RowHammer has a strong physical correlation. There are certain physical regions of DRAM that are much more vulnerable than others. Now, this could be used from the attacker's perspective to attack those regions, but also from the defender's perspective to defend those regions much more aggressively, and those other regions less aggressively. So as I said, all of these observations can be used to create effective attacks as well as more effective and efficient defenses, and the paper discusses that. And it's important because if, for example, with the aggressor rove active time, the assumption may be that when you're creating a defense, you may be assuming that the attacker is activating aggressor roves as frequently as possible. But that's not the worst access pattern, actually. If the attacker keeps aggressor roves active for a longer time, this leads to a much worse access pattern and leads to earlier bit flips with RowHammer. You need to do a smaller number of activations, basically, to get a bit flip. Now, if the RowHammer defense is configured, not taking this into account, but assuming this sort of access pattern, an intelligent attacker may use the second access pattern and lead to bit flips, essentially compromise the system. That's why this sort of understanding is really important, in my opinion. And I don't believe that we have a very strong understanding of these issues currently. But of course, these papers make a dent towards building that understanding. Okay, so spatial variation, I'm not going to go into a lot of detail, but there's huge spatial variation, as you can see in this figure. Different DRAM rows are vulnerable in different ways. For example, in this particular module, some rows require hundreds of thousands of hammer counts to get a bit flip. Some rows require less than 50,000 hammer counts. And that's true for all of the modules, as you can see. So there's a huge variation between DRAM rows. That's true for all of the manufacturers. And there's also a huge variation across different columns. Again, I will not go into the details of it, but certain columns are a lot more vulnerable. This is because of manufacturing variation and some other effects that we don't completely also fully understand. There may be some systematic variation that we cannot completely figure out because we don't know exactly what's going on inside the DRAM chip, but there's this variation that exists. Now, if you understand this variation, you can actually make the defenses much more efficient. Some of the defenses, I'm going to discuss BlockHammer in a little bit, but there are also other defenses that are developed like graphene. These are basically, graphene, for example, uses some frequent item counting algorithms, and it uses some content addressable memory to keep track of frequently activated rows, and it requires a lot of area. Now, if you target these defenses so that they target these vulnerable DRAM rows much more than the less vulnerable DRAM rows, you can reduce the area cost of these defenses. And this is actually very interesting going forward. We sketched that this could be doable potentially, but it requires a lot more work to actually make it work. Okay, I'm going to skip the temperature over here. But there's a lot more analysis in the paper, and you can take a look at it if you're interested. I believe this sort of studies are more important to do going into the future because the problem is getting much worse into the future. So there's a little bit more analysis that we've done this year on word line voltage. And clearly, we built more infrastructure to actually do this so that we can actually change the voltage at very fine granularity and temperature at very fine granularity also. And the key takeaway here is that you can reduce the word line voltage. This is the activation voltage, essentially. This reduces the RowHammer vulnerability, but it also has some side effects, like increasing the activation latency and reducing the data retention time, because voltage really affects the latency as well as the retention time in cells. But in this paper, we show that you can mitigate these in most DRAM chips. So by reducing the word line voltage, you could actually reduce the vulnerability a little bit. You cannot completely get rid of the vulnerability, unfortunately. So this is not a solution by itself, but could be part of a solution in the field. Okay, now I'm going to talk about some new RowHammer solutions and the RowHammer solution space in general. But feel free to, again, ask a question if there's a question. And I hope you can hear me and the internet is okay.
Yes.
Okay, so I got the confirmation. So if there's no question, I'm going to continue with solutions. Okay, so I'm going to talk about especially the BlockHammer solution. This is a solution that we developed in the 2020s. It was published in 2021. And it's a purely memory controller based solution. But let me cover the solution space a little bit more vigorously over here. Essentially, you can build more robust DRAM chips, use error correcting codes. You can increase the refresh rate. Unfortunately, these two solutions are not that great, as we discussed. People have also proposed solutions like physical isolation. You can actually do this at the operating system level or virtual machine level, isolate victim rows and aggressor rows. It turns out these are not completely secure for reasons we discussed in multiple papers, and actually earlier papers also discussed this. And also they're not very memory efficient. So you need to add a lot of isolation rows to protect the victim rows. Victim rows may be rows that are housing security critical data. The two solutions that have emerged as, let's say, very popular and useful and low overhead have been reactive refresh. We've seen an example of it, like probabilistic adjacent row activation is a probabilistic version of reactive refresh. You basically keep track of aggressor rows or probabilistically guess aggressor rows and refresh victim rows. And proactive throttling. Proactive throttling is proactively throttle rows that are activated a lot, like BlockHammer proposes. Unfortunately, the space is complicated. So all of these have cost, power, performance, and complexity issues. And there's no solution that exists that currently scales to very small RowHammer counts on the order of hundreds, for example. What happens if you get bit flips after 128 activations? These are activation counts that actually benign applications may actually lead to today. So it's good to think about it because we're marching toward that regime today. So let me talk about the solution, BlockHammer solution very quickly. So we wanted to solve two key challenges over here. Scalability with worsening RowHammer vulnerability. We want it to be still effective as RowHammer vulnerability scales into the future. And we want it to be completely compatible with commodity DRAM chips. We didn't want to change anything in the DRAM interface and the DRAM chips. So this is a completely memory controller-based solution. So our goal was to prevent actually RowHammer without knowledge or modifications to DRAM intervals. This means that you cannot use reactive refresh because reactive refresh requires you to refresh victim rows. And from the memory controller's perspective, as we discussed earlier, you do not know exactly which rows are victim rows because there's some internal remapping of rows that happens in DRAM that's opaque to the memory controller. So the memory controller doesn't know the physical adjacency of the rows in DRAM. So you cannot use victim row refresh, essentially. So the idea in BlockHammer is to selectively throttle memory accesses that may cause RowHammer bit flips. So you don't refresh victim rows, but use throttle memory accesses to aggressor rows, essentially. So the key idea at a high level is to detect RowHammer attack or aggressor rows that are activated a lot using area efficient Bloom filters. The paper discussed exactly how to do that. And selectively throttle accesses to those heavily activated rows from within the memory controller, slowing down accesses there essentially, such that bit flips do not occur. You can optionally inform the system software about the attack also because it turns out these detection mechanisms in the Bloom filters are quite accurate. You can accurately detect a RowHammer attack compared to a benign application. And this is compatible with commodity DRAM chips. So I'll go through this relatively quickly, but we have two kind of components. Row blocker tracks row activations, as I said, using area efficient Bloom filters. Blacklist rows that are activated at a high rate, and throttles activations targeting blacklisted row. The key requirement is to ensure or guarantee the invariant that no row can be activated at a higher enough rate to induce bit flips. And we have a security proof in the paper. Attack throttler identifies threads that perform a RowHammer attack. So basically, if you're under attack, you can figure this out. And it reduces memory bandwidth usage of these identified threads and optionally reports them to the system software such that the system software can take some other action at a higher level. So this greatly reduces the performance degradation and energy wasted of a RowHammer attack when it's happening. And this is actually one distinction from prior solutions. Prior solutions usually don't throttle the attacks as significantly. And you can see that the performance of BlockHammer is similar to prior solutions that do refresh, except it doesn't require internal knowledge about the DRAM. And when a RowHammer attack is present, BlockHammer is actually quite much more effective than prior solutions. And in the paper, we actually have a lot more. I'm not going to bore you at this point because we don't have a lot of time and it's more detailed than we want to talk about. But basically, we've released a source code of this, and you can actually look at our implementation, and we cover 14 different types of solutions. And we actually evaluate RowHammer protection in terms of 4 desirable properties that, again, I'm not going to talk about in detail, but we've covered some of these. And we show that BlockHammer is the only solution that satisfies some of these properties. But this needs to be evaluated in the presence of solutions that were developed since BlockHammer also. There's actually a lot of solutions that are developed since then, which I will briefly mention soon. There's more in the paper. If people are interested, it's actually quite interesting. There's hardware complexity analysis. Unfortunately, the solution is not simple. Basically, it's area efficient, yes, but it's not efficient enough, in my opinion, especially when the RowHammer vulnerability scales to hundreds of hammer counts. So we show that this works okay for 1000 hammer count, but with 128 hammer count, for example, or 100 hammer count, it may not be very good. But again, this is a good starting point. If people are interested in doing research in RowHammer, they can download the source code, and it comes with BlockHammer source code as well as 6 state-of-the-art mechanisms that BlockHammer compares to. So this is an example of an intelligent memory control. Essentially, I've given you some examples, but probabilistic adjacent row activation was one example of a slightly intelligent memory control that does probabilistic protection. Here, BlockHammer is a more heavyweight example where we use Bloom filters to keep track of aggressor rows, and basically throttles the aggressor rows such that hopefully you're secure, safe, and reliable, and can scale to smaller technology nodes in DRAM. Okay, so that was BlockHammer. Actually, this slide is a little bit out of date because there are other solution approaches that were recently introduced, and these are row migration based. They're actually interesting. The idea here is to dynamically remap an aggressor row to a different physical row before RowHammer bit flip occurs. This doesn't require refreshing victim rows, similar to BlockHammer, and relocates the aggressor row's data. I think this is a heavy-handed solution if you actually do it through the memory controller, because it requires copying data from one row to another row. But if you have in-DRAM support, DRAM support to be able to do this, you can actually reduce the overhead. So this is interesting to examine. And actually, the combinations of these solutions are actually quite interesting to examine, in my opinion. And there are a bunch of papers that are written about these row migration or row swap-based mechanisms. And you can take a look at some of these works if you're interested. Okay, there's more to talk about in RowHammer. I'll give you a quick overview of the field in terms of what happened in 2020 and 2023. And then we're going to take a historical perspective and then conclude. But if there are any questions on solutions, I can handle them now. I hope you can still hear me.
Yes, you can.
Okay, I don't hear questions, so let me quickly go over. So there's a lot of interesting things that are happening in 2020. As you can see, IEEE Security and Privacy had a dedicated session on RowHammer with 4 works in 2020. And major security conferences, operating system conferences talk about interesting things about RowHammer. I'm not going to cover a lot of these. This work, for example, introduces an automated way of doing RowHammer attacks through JavaScript, which is quite interesting. Clearly, there are architecture conferences that are proposing solutions. This was this year or last year, Security and Privacy. They're both solution papers as well as defense papers. You can see there are actually neural network attack papers. This Deep Seal is an interesting paper. Here, these folks show that using RowHammer, you can steal the weights and figure out what are the weights used in a private neural network, which you may not want to expose to others. Again, this is a confidentiality breach using RowHammer. And as I said, there are solutions that are proposed in recent conferences as well. And there are folks in industry arguing that we should be more open about what's going on in DRAM to the higher levels of the system stack so that we can protect these issues in the system stack much better. Google, for example, introduced another type of RowHammer that's actually quite interesting. You hammer a far away row a little bit, a lot, and you hammer an adjacent row just a little bit. And this way you can actually induce bit flips in a row adjacent to the row that you're hammering a little bit. This is interesting because this bypasses a lot of the attacks, a lot of the defenses that were developed previously. And this actually some of the defenses that actually do refreshes can lead to attacks as well. So defenses can be leading to bit flips. And this paper talks about that. It's quite interesting, I think. So as technology scales to smaller nodes, we will see a lot of other interactions like this, in my opinion, and we need to understand things better. And again, there are other works that I'm not going to talk about because we don't have time. These are some of the works that we have been also doing. This work appeared at Micro last year, and it showed that you can actually parallelize refreshes with accesses in DRAM, in real DRAM chips, and hide the latency of some of the RowHammer defending refreshes. And I believe reducing the refresh latency and refresh overhead is going to be a lot more important for RowHammer defenses into the future. And we've also been arguing that you need transparency in DRAM so that you can expose DRAM information a lot more to the memory controller and the system stack so that you can prevent these issues in a much better way at the system level. We've also been proposing the idea of self-managing DRAM chips. I will mention this briefly. because I think this is a step in the right direction also, because some of these operations, in my opinion, are best handled in DRAM. Unfortunately, today's DRAM doesn't have freedom to handle these things internally. Today, what happens, we have a very tight coupling between the memory controller and DRAM. Memory controller sends a command to DRAM and expects a result within some time. DRAM has no freedom, no breathing room to say, okay, I'm doing something internally, don't disturb me for a while. The idea in self-managing DRAM is exactly that. Prevent the memory controller from accessing DRAM regions that are under maintenance by rejecting row activation commands. So we basically add a very simple modification to the DRAM chip and the interface saying, you can negative acknowledge some command, and the DRAM chip can reject an activation, for example. Internally, it can do RowHammer maintenance, or internally, it can do some smart refresh mechanism or some smart memory scrubbing mechanism. And that's the idea over here. In this paper, we actually look at refresh, RowHammer protection, and memory scrubbing, and we show that you can prevent RowHammer, and you can make these maintenance operations much more efficient by having this breathing room in DRAM without any further changes to the DRAM interface and memory controller. So I think it's also interesting from the historical perspective, because initially there was asynchronous DRAM, and over time we moved it to synchronous DRAM, where memory controller in a very tightly controlled way manages DRAM. This gives some asynchrony to the DRAM such that DRAM can do some operations by itself, while the memory controller can do some other operations by itself. So going into the future, I think we really need to revisit the duties that we place to the memory controller as well as the memory chips. And I think it's going to be even more important when we do processing in memory. Last year in this research symposium, I talked about memory-centric computing. I think we need better interfaces. I also mentioned that we need better interface for memory-centric computing. If you do processing in memory, you need to give more freedom to the DRAM chip. And I think this is along the same lines. Okay, if you're interested, one of my PhD students who's recently graduated talks about this in this particular talk. So there's a lot more in our preprint as well. So RowHammer is not done yet. People are working on it, both in industry and academia. And you can see that this is coming up in May this year. You can see that there are interesting defense mechanisms that are being published in security conferences. And in HPCA, there are also defense mechanisms that are going to be published. So I believe there's more to come, clearly. Let me give you now a quick perspective on future challenges, and then we're going to conclude. I believe future is going to be a lot worse, basically, because DRAM is becoming less reliable and more vulnerable. There could be other problems that may also appear, or they may be going unnoticed. We're working on some of these issues. I believe other people are working on some of these other issues. These errors can pose security vulnerabilities. And RowHammer is clearly becoming worse, but there could be other problems as well. And you may say that, okay, there are other technologies that are not vulnerable, but unfortunately, that's not true. Flash memory is actually a lot more vulnerable than DRAM, and emerging technologies all have their problems. In fact, some of the works have shown in simulation that RowHammer exists in some of these other technologies as well. And this is from one of the papers that we wrote about flash memory. There are many, many errors, and there are many, many mitigation mechanisms that are employed in real SSDs, which I'm not going to go into. I believe DRAM is going to be similar going into the future as we scale the technology to very smaller technology nodes. And I believe we will need intelligent controllers, and this is already happening in the field, both inside the DRAM chips as well as outside the DRAM chips. And I think we will need to revisit this. And they can enable avoid many failures and enable better scaling. But I think we really need to understand more. We don't understand enough, in my opinion, as I mentioned earlier. We need to develop better methods for vulnerability modeling and discovery. We need to model and predict based on real device data. And we want to understand these vulnerabilities better so that we can protect against them completely securely. And we also need reliable metrics. On top of this, we need to develop solutions that are principled with security as key concern. We need to have good partitioning of duties across the stack between DRAM and memory controller, between memory controller, hardware, as well as the system software, for example. And I think these really need to be examined going into the future. Most importantly, we cannot give up performance and efficiency, but we also need to be secure at the same time. So that makes it a tough problem. I believe patchability in the field is important. If we can patch the memory controllers, for example, just like we patch the software, we can solve these issues much better into the future, and we can anticipate some of the unforeseen consequences also. Design and test in the field is going to be a lot more important because we may not be able to fix all of these errors when we design the hardware. Over time, doing online testing, we might discover the errors, and by patchability in the field, we can cover for these errors. So I believe there's an interesting set of research to be done, and people are doing part of it, but there's more needs to be done over here. In terms of RowHammer, I think understanding is going to be critically important. There are many effects that still need to be rigorously examined: aging, environmental conditions, memory access patterns, memory control and system design decisions. How do they affect RowHammer? How do they make it better or worse? Effect on benign applications. These are actually very interesting things that need to be studied. But of course, solutions are really important, and specifically, flexible and efficient RowHammer solutions are necessary, in my opinion. And we need to co-architect system and memory as well, as I mentioned earlier. Now, we actually argue for these solutions in our recent invited paper. If people are interested, this is a relatively short paper that talks about what has happened in RowHammer relatively recently. And I believe there needs to be better communication between DRAM and controller, as we have discussed. So understanding requires real experiments, as I said, and these are some infrastructures for those. And if people are interested, we'd be happy to share actually our expertise in the infrastructure. And if people are interested in doing studies, we'd be happy to share. If you can download the source code, of course, but if you need help, we're happy to help. Okay, let me go back to the picture that I showed you earlier. This is a bridge. This is the Tacoma Narrows Bridge that incurred a bit flip in 1940. And we did not really solve the problem, basically. It's like RowHammer. This is 1994 in Korea. Actually, there were fatalities on this one. This is 2017 in Minneapolis. This is 2018 in Genoa. So we get bit flips, and in our critical infrastructure, as you can see. And this is more recent. This is closer to my heart. This is in Pittsburgh. This used to be a bridge that I went over many, many times when I was at Carnegie Mellon. And these are actually very nice pictures. Unfortunately, not so nice for people who were inside those cars, but nobody got wounded in this particular case, so it was lucky. So we have not, human beings have been building bridges for thousands of years, and clearly we have not gotten it completely right. I don't believe we're going to get computer infrastructure right also in terms of bit flips. We're going to have a lot of reliability issues, but we can actually patch things better compared to the bridges. It's going to be very difficult to do in-field patchability in bridges, but in computing, we're much more softer. So we can avoid such failures much better in computing systems. So I believe in computing systems, we need to take a much more rigorous approach than what we do in bridges today. And I believe we can solve it much better. So that brings me back to the to earlier papers that I mentioned. We argued for this earlier. I actually think that after doing like more than a decade of research in these issues, we really need to have a more systems perspective to solve the issues at the device level. These devices are not going to get better. We really need to solve the problem at the systems level, architecture level, both hardware and the software, to fix the issues. And let me mention that industry is finally acknowledging RowHammer. This is a paper that they wrote in 2014. At that point, they did not acknowledge RowHammer, but more recently, they're a lot more open. But they actually talk about similar solutions. So this is a paper that was written by Samsung and Intel together, two companies that don't talk with each other at the time. I don't think they talk a lot today also, but they basically argue that these issues are not going to get better, so we should really co-architect controllers and DRAM together. Okay, let me give you some final thoughts on RowHammer and conclude, and I'm happy to take more questions. And to give you final thoughts, I will go back to 1980s. This is a slide that I borrow from Satya, who's a distributed systems person at CMU, who was my colleague. And he uses RowHammer as an example of Byzantine failures. Many of you probably know about Byzantine failures. That was introduced by Leslie Lamport in this seminal paper. These are characterized by undetected erroneous computation. You get an error, basically, and your system these errors can be used maliciously, and it's very difficult to detect and confine them. This could be a reliability problem. This could be a security problem. And basically, if you would like to trust your system, you really want to do all you can to avoid these Byzantine failures in the system. And I'm sure a lot of people are familiar with this, but this is the original paper that introduced the Byzantine generals problem by Leslie Lamport. Now, I will also go back to, and RowHammer is an example of a Byzantine failure. It's an error, but it could be used maliciously as well. I will also go back to one paper. These bit flips worried a lot of people. This is a paper from IEEE Security and Privacy from 2003. These folks, it's a beautiful paper actually, showed that by inducing errors in memory, you can take over the Java virtual machine as a user-level program running in the virtual machine. Now, these folks were clever. They did not have RowHammer at the time. They induced bit flips in memory using this lamp. You can see this lamp. This lamp actually heats memory and induces a lot of memory errors, and they figured out a way of taking over the Java virtual machine. This is very similar to the attack that the Google folks used to take over the Google native client in 2015. Now, this was before RowHammer, and this paper is very interesting. Clearly, I read it a lot before I worked on RowHammer, but a lot of people did not think that memory errors were actually really bad. So what RowHammer showed was a simple memory error can be induced by software. You don't need that lamp. You don't need that physical access. You can be remotely accessing some computer and taking over it because of memory errors. So that has enabled a renewed interest in hardware security attack research, actually, and also defense research more recently. Real memory chips are vulnerable, and this causes real security problems in a very widespread manner. And hardware reliability and security connection is now mainstream discourse. And as a result, you basically can recover private keys in RSA, for example. As a result, people have been developing many new RowHammer attacks. Clearly, many papers have been published, and there's more that is coming up. And more recently, there's more emphasis on new RowHammer solutions. That's great, I think. And as I said, papers are coming up in 2023 on talking about RowHammer solutions as well. I believe principled system DRAM co-design is going to be a lot more important going into the future, but there are more solutions to come as well. So most importantly, I think this RowHammer, the existence of these bit flips, enabled a shift of mindset in mainstream security researchers, showing that general purpose hardware is not trustworthy. It's fallible in a very widespread manner, in a real manner. Its problems are exploitable. So as a result, many researchers have been looking into hardware security more recently and trying to find the root of trust in hardware. Many system security researchers examined hardware in more depth. And it's very interesting that two of the groups that discovered Meltdown and Spectre, which are CPU security vulnerabilities, essentially side channel vulnerabilities, they worked on RowHammer heavily before. So there's an interesting connection between, I think, these different types of vulnerabilities that exist in hardware. And I believe there's more to come in this space also, as we have been seeing in with the focus on processor vulnerabilities more recently. So to conclude, main memory reliability is reducing. Reliability issues open up security vulnerabilities, and these are very hard to defend against. As I said, these are Byzantine failures, as Satya puts it in his CMU classes. RowHammer is a prime example of this. It's the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. And I think it's quite exciting to see its implication on system security research, but more generally systems research as well. The bad news is this is not going to get better. RowHammer is going to get worse until we transition to some other technology that makes it better, hopefully, but that's not on the horizon yet. The good news is we have a lot more to do as systems and security researchers and architects. We're now fully aware hardware is easily fallible. We're developing both attacks and solutions, and we're developing principled models, methodologies, and solutions. And I think those are very, very important for building and understanding is very important, as I mentioned. And I will conclude, if people are interested in getting into this area and they may not think that they know a lot, I would recommend looking into this retrospective paper that really covers across the stack, and more recent update that we have to that paper in this invited ASP DAC paper. And there are also lectures we have online. And I will acknowledge people who have supported this research. Many companies actually have supported it directly or indirectly this research. And most importantly, I'll acknowledge my group who've done this research over more than a decade right now. And you can put some faces over here, and some newsletters exist. We need to actually release the newsletter for 2022, which has not happened yet. And we cover RowHammer in detail in our lectures. You can take a look at especially two lectures that talk about RowHammer, as well as exploration of emerging memory systems using Ramulator, which is related to RowHammer. And at this point, I will stop. I'm happy to take more questions. And thank you for bearing with me in this difficult weather in Athens. I wish I could be there, but hopefully next time.
Thank you, Anu.
Thank you.
Let me coordinate a little bit the Q&A session. Are there any questions? Yes, yours.
Okay, thank you, Anu. Thanks a lot. That was a fascinating talk. So I have a few questions, but I will start with just one, maybe to warm up a bit the discussion. Hope you can hear me. Can you hear me?
Yeah, I can hear you. It's a bit far away, but I'm decoding.
Okay, so the first question is that during the years you have done quite a lot of experimentations with various devices, right, from various vendors, and you have seen maybe different behaviors. Some of them are less vulnerable, and some of them are more vulnerable. Are there, let's say, high-level or more lower-level features of those devices that behave better? For example, are they more expensive? Do they consume more power? Do they come from a specific vendor? Have we seen some patterns, high-level patterns of behavior, so that maybe this could guide us towards a solution?
Yeah, that's a great question. So in terms of cost, no, we don't see any correlation, frankly. The biggest correlation is if the vendor, for example, has a device that's more cutting edge, scaled more into the future, likely denser, but not necessarily denser also, those are the devices that see more errors. So the vendors that are actually at the more cutting edge of the technology, based on what we can infer, of course, seem to be more vulnerable. So we don't see any correlation between vendor other than that. Different vendors are almost equally vulnerable, assuming similar technology nodes that they're at. Now, power is interesting. That's something we have not looked at as much. That's something that I think there's a paper that's coming up in one of the venues, or maybe that was presented this year, that looks at the correlation between power and RowHammer, and you can take a look at that. But again, yeah, I think it's a bit hard to correlate these results based on what we see immediately with power. So it could be another artifact if there's some correlation between power. But the strongest correlation is really with the technology node that we see.
Okay, thank you.
You're welcome.
You want to go ahead? Any other question?
If someone is willing to give up performance, are there ways that you can create a system that is RowHammer free?
Yeah, I mean, certainly, yes. If you want to give up performance, the solutions that I mentioned, for example, BlockHammer, is if BlockHammer actually, there are a bunch of solutions that are completely RowHammer free, and normally they don't have performance overhead also, except they don't scale well into the future. So in the future, you can give up performance and you can use those solutions and you'll be RowHammer free. Now, in order to make sure that you're RowHammer free, I think you need to configure your RowHammer solution to be conservative, meaning it needs to, for example, refresh or throttle earlier than it should. So you give up even more performance than you should probably. But yes, so the answer to your question is directly, absolutely yes. But then not many people want to give up performance for security. Ideally, the tough research problem is figuring out how to get both at the same time as much as possible. But I don't believe, for example, increasing the refresh rate, at least the way we currently do refresh, is going to be acceptable under any condition, because we showed in our work that you give up performance so much, like 10x. But some of the other solutions, yes, I think some of the other solutions can be perfectly secure if you give up performance.
You did testing on DDR3, DDR4 memory. How about DDR5? Or
okay.
testing on graphics memory, like DDR5, DDR6, or HBM?
Yeah,
these are memories, yeah? Okay.
Yeah, that's a great question. So, so we have not done testing on graphics memories. We have done some recent testing on HBM, and we see RowHammer issues. It's very hard to test all kinds of memories because it requires you to actually have this infrastructure developed for different memories, and we don't have access to DDR5 at this point. I believe other people have tested DDR5, but there's no infrastructure like what we have to really understand RowHammer for DDR5 yet. Now, that said, there's no reason to believe that RowHammer is actually not present in any of these memories, because the core of DRAM is essentially the same in all of these memory technologies. If you look at the array structure and internal organization, it's very, very similar. It's the interface that's different, and it's how we actually, let's say, do the row buffer sizing, etc. Those are different. Essentially, there's no reason to think that RowHammer is not vulnerable. The question is, of course, how vulnerable are different types of memories, and are there different effects that make RowHammer worse in, for example, HBM, because you have 3D stacking and different stack layers may affect each other. So there are actually interesting questions to be asked in different memories, but I don't believe that there's any reason to believe that any of these memories fundamentally are not vulnerable to RowHammer. In fact, for example, RowHammer standards, RowHammer solutions from DDR5 are being applied all across the standard space for different types of memories today. For HBM, for example, HBM 3.0, I believe, uses exactly what was developed for DDR5 with some small modifications.
Okay, other question?
Okay, I have another one on also. You mentioned a lot about attacks and attackers. So do we suffer from RowHammer only from handcrafted malicious attacks, or do real applications also expose similar, patterns, and we can suffer from the RowHammer, let's say, problem from some, code snippet in a real application?
Sure. I think that's an outstanding question. Thank you. So there are two answers to it. One is I don't completely know, but I believe the answer is yes. Actually, there's some anecdotal evidence. When we were doing RowHammer, even at the time in 2012, we actually talked a lot with industry, and there were some cases where industry tracked some of the failures in their data centers to RowHammer-like access patterns in real applications, even at that time. And at that time, it required like hundreds of thousands, more than around 100,000 activations to induce bit flips. So it's of course not easy for a real application to induce a bit flip, because there are many, many layers of caching inside the DRAM as well as outside the DRAM today. So these real applications should be doing some sort of synchronization, for example, on the memory side with uncacheable structures. And this was the anecdotal evidence that we had at the time to actually induce many, many row activations on the memory side. Today, I think it's more probable that benign applications, that real applications have these patterns that lead to RowHammer, because the number of bits, the number of activations that an application needs to do is only within the order of thousands. And this is imaginable. We actually look at a bunch of applications, and today some of the applications can get to that number. And if RowHammer scales to the future, if we get bit flips after 100 activations, now the number of a fraction of applications that are going to do 100 activations within a refresh interval of, let's say, 8 milliseconds, let's be aggressive over there also, is going to be a lot more. So I think maybe today not many applications suffer from it, but we may not know it also. But in the future, I think it's going to be a bigger problem. What you mentioned is going to be a lot bigger problem than what we may not know exactly today. Hopefully that answers your question. Unfortunately, yeah. I cannot give you an application that actually induces bit flip, but with talking with industry, we have actually seen that they were actually very worried, because they have seen some anecdotal evidence on this that they don't necessarily want to share.
Okay, thank you.
Sure, you're welcome.
Yeah. Onur, let me ask one too. From testing, we knew a long time ago that closed cells are related when you look for weak cells, and there's a pattern-based sort of testing for memories, for memory arrays. But that sort of behavior was well understood. What's difficult with RowHammer, and we don't have the physical model that explains it, other than the remapping of rows, but which I think is static for the chips, or not?
Okay, so that's a very good question. So hammering patterns, for example, the testing programs that were developed, they had some marching patterns, clearly that used to test memory to basically identify this sort of interference. But before people showed that RowHammer, and also there were certainly works in 2002, for example, the Rediker work showed that there's word line coupling in DRAM. But unfortunately, because those word line coupling effects were not that bad, there were no testing programs that were developed to test specifically for hammering a given row. As a result, people did not develop tests. And after our paper was published, the memtest company, memtest 86 program, was modified to actually develop these hammer tests. But even then, those tests were not comprehensive, which is interesting, actually. So these tests are actually very expensive tests because you need to test every single row hundreds of thousands of times to actually induce these bit flips to decide whether a row is vulnerable. So testing is actually very, very expensive. It's doable, but extremely expensive. Now, in terms of modeling of which rows would be vulnerable, I think that's a great question. Can we somehow do some low-level device modeling to figure out which rows are going to be vulnerable and protect it without testing, protect them without testing? There are some papers that try to look into that direction. We actually referenced them in our survey from 2019 and also in our ASP DAC paper. If you're interested, I'd be happy to point them to you also. But unfortunately, that modeling is also not comprehensive. And some of those models are not very well validated with devices. So if you go into a little bit more detail, there are a bunch of effects that lead to RowHammer. One is word line coupling, but there are also some hot carrier effects, and there's also other coupling effects that happen between cells. And a lot of these become difficult to model. And also, there's also the other dimension. Even if you can perfectly model them, you need to have the parameters that are required for most recent technology nodes that only DRAM manufacturers may have or may not completely have also. So that makes it difficult, basically. So you may, as a system designer, you may want to model these things, but you may not have complete information. And also the situation is much more difficult than faults that happen because you have some interference between two different cells without this hammering pattern. I don't know if that answered everything that you asked, but hopefully that gives an idea.
Yes, thank you. Do we have any other question?
Yes. In switch, so you can see me. I hope you can hear me from
Yes.
Yeah. So I have actually two questions. Small one. I think RowHammer is a perfect example of a side channel attack. Am I right?
So not, I wouldn't call this a side channel attack. I would call it essentially a fault attack. Basically, you can induce a real fault. You can corrupt data, basically, or data corruption attack, whatever you want to call it. But this data corruption can be used as a side channel also, as we discussed in one of the confidentiality papers. For example, the RAM bleed paper uses this data corruption as a side channel to get information. But the data corruption can be used as a data corruption itself without actually leaking some information.
Okay. And secondly, I guess caches are also vulnerable to RowHammer. But I think that RowHammer in a certain level of cache does not change the entire memory hierarchy of that exact bit, let's say. So could we use the information from the higher or lower level of the memory hierarchy to tackle the problem? I guess not, because we don't know if the RowHammer has happened, right?
You mean in the caches, in the SRAM caches, in the processor?
Yes.
Yeah. So okay. Yeah, that's a good question, basically, whether SRAM is vulnerable to something like this. So in the original paper we wrote in 2014, we say that different types of memory have this sort of vulnerability, essentially RowHammer read disturb vulnerability. And it's true that SRAM is also vulnerable to read disturb in a slightly different way. But existing caches are very difficult to, it's very difficult to show that in existing real systems, I would say, because existing caches have a lot of protection, error correction, on chip. As a result, I believe those vulnerabilities cannot be, let's say, I don't want to say it completely unexploitable, but cannot be easily exploited. in real caches. But it is true that fundamentally SRAM is also vulnerable to similar read disturb effects. In fact, Flash is also vulnerable to read disturb effects.
Thank you.
You're welcome.
I think that should be it because we're running out of time. Thank you very much, Onur, for the great keynote.
Yeah, thank you,
Yeah.
Genesis.
Yeah.
Okay, so we have a break now for a little more than 15 minutes. Onur, thanks a lot. I suppose it's time for you to rest now, right?
Thank you very much. Enjoy the rest of the conference.
Okay, thanks a lot. Bye.
Bye-bye. Thank you.